In this video, we're going to explore thermochemical calculations a little bit more in a little bit more detail, or a little bit more depth. So we're going to have a look at this equation here. I'm sorry, it doesn't quite fit in the screen. Everything in orange there would be the data we're given in a question. So we've got the balanced equation, we've got the enthalpy change down the bottom, and we were given the molar masses of everything in there. And in this particular question, we will be given the mass of aluminium consumed by this chemical reaction. From that, there's a lot of things that could be asked. We could ask how much iron 3 oxide is required to make this reaction be completed. We could be asked the mass of iron produced, the mass of aluminium oxide produced, or something like that. And of course, we could be asked how much energy would be released by this reaction. So, going by our previous steps, the first thing we would do is we would calculate our amount of aluminium, because from there we can actually work out just about anything else, and that's what I want to show you in this video. Yes, we can work out the amount of energy produced, but what I can also do is show you how much of the other substances are involved in the reaction. Now this would be more if we are being asked more than one thing in this question. So the energy produced, and then it might say how much aluminium oxide, or what mass of aluminium oxide was produced, or what mass of aluminium oxide and what mass of iron would be produced. Those are the sorts of things that we would want to know. So here we go. Step one would be to work out the amount of aluminium, and that is the mass divided by the molar mass. So I go 67.5 divided by 27, and I get 2.5. Now I need to be careful here. Everything in this table is 3 significant figures, so 3 numbers to show its precision. So I need to give this one to the same level, 2.50. I'm sorry, I'm not going to put the unit, it is moles, but there would be my answer there. Now, there's 2 aluminiums in this equation, but there's only one iron oxide, or ferric oxide, and there's only one aluminium oxide. So the amount of those will be half as much. So that's quite an easy calculation to work out how much of these 2 there are. So I'm going to divide 2.5 by 2 and get 1.25. Because there's 2 aluminiums and 2 irons, that's the same number, so the ratio is 1 to 1. There would therefore be 2.50 moles of iron. Hopefully now you can see that I haven't got very many unknowns. I can actually find the mass of all of these by rearranging n equals little m over big M. I can rearrange it where our unknown is going to be mass. I'm just going to slide this down so I can show you the quick working of that. So if n equals little m over big M, or over mr, and I want to make mass my subject, I multiply by molar mass on both sides. So it becomes mass equals the amount times the molar mass. So slide myself back up, and I'm going to do that calculation. Basically the top number times the middle number. So 1.25 times 160 is 200. So this would actually yet need 200 grams of iron 3 oxide to fully to allow for the 67.5 grams of aluminium to fully react. So you'd need at least 200 grams of this. It would make 1.25 times 102, there's my 102, it would make 127.5 grams of aluminium oxide. Now, again, my 3 significant figures means I have to put 128 there. And how much iron would it make? 2.5 times 55.8. 139.5, again have to round it up because it's 0.5, which means that these 2 numbers are not going to add up the same as this. They're going to be a little bit higher. but that's just what happens with significant figures sometimes. So 140 grams of iron would be made through this process. Now, if I'm asked any of those questions about their mass of anything, I've got those in my table. And I can just report those straight away. But what I'm going to do last is, of course, the question that would be asked in a thermochemical equation, which is how much energy would that create? Well, in the equation, it's negative 852 kilojoules per mole. Now, that's got 1 mole, that's got 1 mole. So, for 67.5 grams, there'd be 1.25 moles of it. So all I'm going to do to find the amount of energy, sorry, sliding down again, is I'm going to do my energy is my amount times my enthalpy change, and I'm going to take the absolute value. I'm not going to care that it's negative. So that is going to be 1.25 moles of iron 3 oxide or aluminium oxide, because there's one of those each, times 852. I've got rid of my negative. You can probably hear my calculator going crazy, which is 1,065 kilojoules, but 1, 2, 3 significant figures. Oh, I've run out of space. I'm sorry, I'll slide down. Is 1070 kilojoules. 1, 2, 3 significant figures. This one is only a placeholder. It's not significant. Okay.